Okay, we're happy to have Piotr Gruza back for part two of his talk on separations between categoricity-like properties. Go ahead, Piotr. Oh,
I
you're
need to
muted.
unmute. So thank you for this introduction. As you said, I will continue today's talk I have started uh, last week. So let's start with some reminders. So the talk is concerned with four notions: uh, tightness, neatness, semantic tightness, and solidity. Tightness and neatness are kind of completeness-like properties. Solidity and semantic tightness are categoricity-like properties in a specific sense that, say, if we have a theory that is solid and we have a model of this theory, then there is some surrounding of this model, which is described in a specific way, in which every model of this theory is definably isomorphic to this given model. So in some surrounding, there is only one model in a sense. Uh, uh, what we should recall is, okay, so let's recall that uh, all these properties are closed under extensions. That is, if we have a theory and we have an extension of this theory in the same language, and then if the previous theory is solid, then this extension also is solid, which makes sense on this intuitive level, for example. If we have so on this intuitive level, if we have a theory that is categorical, locally categorical, and we take an extension of this theory, then, well, we have less models. Maybe we shrink a little bit the surroundings, so this should be also still be locally categorical. So all these properties are closed under taking extensions. They're closed also under by interpretability. So if we have two theories, then if first one is, say, tight, then the second one also is tight. If the second one is not solid, then the first one is also not solid. This talk is concerned with the relations between these notions. So we know that solidity is the strongest property, tightness is the weakest, and neatness and semantic tightness are intermediate. And during this talk, I show that all these properties are actually distinct. So last time, I showed an example of a theory that is tight, but is not neat and is not semantically tight. So is complete in a weaker sense, but is not complete like in the stronger sense, and it is not categorical in any of our senses. So the idea was the following. We have choose two models as our intended models, and one of the models was the standard model of arithmetic. In this case, the second one was the so-called second standard model of PA minus. We have taken these two models. We took a theory. Saying this model or this model, and we showed that this theory is tight because these two intended models of our theory are not close enough, but are not. But this theory is not complete in the stronger sense and is not categorical because there is no non-trivial relation between these two models, which are intended models of our theory. And to write this theory, we use the following notation, which we'll use also today. So if we have two theories, A and B, and a sentence sigma, and all are in the same language, then the theory A sum B along sigma is a theory which basically say if sigma holds, then A holds. If not sigma, then B holds. And this is case extension. Case yeah. Okay, so going back to separations, then we focused more on theories that are tied but not neat, so are complete in the weaker sense, but are not complete in the stronger sense. And we showed that we can find stronger theories, subtheories of PA that have this property that they are tied but not neat. And here we have taken, the strategy was the same. We have taken as one of the models the standard model of arithmetic. The second model was, in this case, it was a variation on the one of the classically studied B models. And we showed basically that they are not close enough to break tightness, but they are close enough to break neatness. Okay, and I said at the end of the previous talk that today I will start with an example of a theory that is neat but is not semantically tight. But I decided to omit this example to have more time for the second part, for the things I planned to be in the second part. So today I will show actually that all these separations can be done in the context of subtheories of ZF with axiom of infinity negated with and with the transitive closure and transitive containment axiom added. This is somehow natural direction because we know that ZF with negated axiom of infinity and added axiom of transitive containment is synonymous with PA. So we have a set theoretical counterpart of PA. And we know also that there is relatively easy to build models of ZF with the axiom of infinity negated that have automorphisms of some needed properties. So we will use it today. Actually, I'm not going to show all of these examples. I will show only one example and then comment on other examples. So I will show a theory that is semantically tied but is not neat. And actually, I will focus on the fact that this theory is semantically tied but not solid. So I will show a theory such that this theory has two models, such that, say, N and M, such that N is a retract of M, but there is no definable isomorphism from N onto M. Actually, they just will be not isomorphic. These will be our two intended models. But at the same time, if we have any two models of this theory such that these models are bi-interpretable, then necessarily there is this definable isomorphism from the first one to the second one. So being a retract is not enough to define a map from the first to the second, because we have these two these two intended models, but if we have two bi-interpretable models, then actually they need to be definably isomorphic. Okay, so we need some reminders. So ZF fin is, by ZF fin, I will denote ZF minus with the axiom of infinity subtracted and augmented with the negation of infinity, of the infinity axiom. TC is the axiom of transitive containment, which say basically that for every x, there is y, such that y is transitive and x is contained in y. And it is a well-known result of Richard Kay and Tin-Lock Wang that ZF fin plus TC and PA are actually synonymous. Uh, in words, it can be also stated that these theories has a common extension by definitions. So PA we can extend by definitions, ZF fin plus TC we can extend by definitions, and we obtain the same theory.
Yeah, Piotr, just out of curiosity,
Yeah.
so you have PA on one side and PA is stratified, there are I theories and B theories. Does it go through, is it a stratification of the ZF thin, where those synonymity would translate?
Yeah. Yes.
So it goes level by level somehow?
Yeah, more or less from a level of, I think, I delta 0 plus x, there is more or less direct connection, but we need to be sometimes more careful with what hierarchy in the set theory we take.
Right.
What are bounded formulas?
So this is like through the comprehension axiom, or
I'm not. I need to be now. Okay, is it comprehension axiom or replacement?
replace it, or but one of those, and it's restricted to
Yeah.
complexity.
One
Or
of
I see.
them. Yeah.
Mhm. All
Uh,
right. Thank you.
yeah. But yeah, and actually, to this synonymity is given by the Ackermann interpretation. I think more or less from the level of I delta 0 plus exp. So yeah. So yeah. Oh, okay. So let's go on. So I will show that there exists a semantically tight but not solid, computably enumerable subtheory of ZF fin plus TC that contains ZF fin. We cannot. The point is that we cannot. Well, we cannot easily translate this into the language of arithmetic because, at least using the inverse of Ackermann interpretation, uh, because this will be a theory that does not prove transitive containment. But already aldelta 0 proves that transitive containment holds in the Ackermann interpretation. Yeah, but okay, so we will prove this theorem. Actually, to make this clearer, I will not show directly an example of such a theory. I will show an example of a theory of in a little bit different language, that is of ZF fin with atoms with one additional predicate. And then I will say that basically this theory is bi-interpretable with a subtheory of ZF fin plus TC. Okay, so the strategy will be similar. We will describe two models and one of the two models, and these will be our intended models, and one of these models will be more or less the standard model. And the second one I will describe in a moment. So let's describe this model. So we start with an infinite countable set of atoms. And then inductively we define V0 of A as A, Vn plus V1 of A as Vn of A union finite subsets of Vn of A. And we define V omega of A as the union of all Vn of A's. So basically, this is a cumulative hierarchy built on these atoms. And we give, okay, so we take this set, we take one binary relational symbol, and we say that extension of the symbol is standard membership relation on V omega of A, but we assume that A are atoms. Okay, so we have V omega of A, and now let this wave be an equivalence relation on A such that every equivalence class of this wave relation is of prime cardinality, and for every prime P there is exactly one equivalence class of this relation of cardinality P. So basically we divide A onto equivalence classes of prime cardinalities such that for every prime we have an equivalence class of size P. And now we take a fresh binary symbol, relational symbol, and we define an extension of this symbol on V omega of A. And we do this by saying that P of xy holds if only if first x is an atom, and secondly there exists such a prime that an equivalence class of x is of cardinality P, and y is the pth ordinal in V omega of A. Of course, we make this definition externally because this is not definable in V omega of A with a membership relation. Okay, and we will say later that an element A, which is an atom, is a P atom if P of AP holds, where P here is again pth ordinal in the structure. So our first intended model is M0, which is basically V omega with the standard membership relation, and the extension of the symbol P is empty. MA is V omega of A with the standard membership relation, and the extension of P is as I described 30 seconds ago. So I claim that there is a semantically tight but not solid computably enumerable subtheory of the sum of the theories of M0 and MA along some sentence C. And then I claim that there is a subtheory of ZF-fin plus TC that contains a ZF-fin, and that is bi-interpretable with the theory from this previous theorem. So now, because we know that semantical tightness and solidity is close undertaking under bi-interpretability and undertaking extensions, so we know that this subtheory of ZF-fin plus TC is actually a computably enumerable subtheory of ZF-fin plus TC that contains ZF-fin, and that is semantically tight but not solid. But in this talk, I will focus on this first theorem. And actually, I will omit this part with computability of this theory, and I will show that basically this theory is semantically tight but not solid. This theory, we say this complete theory or this complete theory. Okay, so let's prove this theorem. We need to prove two things. We need to prove that this theory is not solid, but is semantically tight. So let's first prove that this theory is not solid. So we need to find two models of this theory such that first model is a retract of the second model, but there is no definable isomorphism from the universe of the first model onto the universe of the second model, onto the second model. Okay, so let's prove it. So obviously M0 defines MA. About M0, we can think actually as about V omega. This is V omega with an empty predicate added. So we can think also about M0 as about just the standard model of arithmetic. And V omega of A is basically V omega on countable a set of atoms with predicate added, which can be made computable. So obviously it can be interpreted in the standard model of arithmetic. So we basically in M0. We can also build an interpretation in the opposite direction, namely in V omega of A, we can build V omega. And this is because A is definable in V omega of A because the empty set is definable because this is the only atom that is not in the scope of the predicate P. And now an element is in V omega if in the transitive closure of this element, the only atom is the empty set. So we have this interpretation in the opposite direction. And actually, we know that the composition of those interpretations is isomorphic in M0 to identity interpretation on M0. And this is because, well, as I said, about M0, we can think as about the standard model of arithmetic. And the standard model of arithmetic has the property that if this model interprets itself, then this interpretation needs to be definably in the standard model isomorphic to the identity interpretation. Basically, we can take 0 and map it onto 0 of the interpretation. And then inductively build, say that we map and build a map saying that we map n plus 1 onto n plus 1 nth element, n plus 1 when n plus first element of the interpretation. And it gives us this isomorphism. And because M0 is in a sense the standard model of arithmetic, but written in the language of set theory, so if we start in M0, we interpret MA in M0, and again, and in MA we interpret M0, then, well, when we compose this two interpretations, we obtain an interpretation of M0 in M0. So there is a definable map from M0 onto this interpreted copy. Okay, so we found two models of our theory such that they are not isomorphic, and first is the retract of the second. And these are basically two intended models of our theory. So we are done. So now we want to prove that our theory is actually semantically tight. And to do this, we'll prove two lemmas. We'll prove that theory of M0 and theory of MA are both solid. And we will prove that if we have a model of theory of MA and a model of theory of M0, then M is not a retract of N. And it will be enough to prove the first lemma. Why? Let's prove it. So say we have two models of this theory. that are bi-interpretable. So we have three options. First, it might be the case that N and M are both models of theory of M0. But then first lemma say that theory of M0 is solid. So we know that there is a definable map from N onto M. So we are done. The second case is similar. So it might be the case that N and M are both models of theory of MA. Then again, second lemma says that theory of MA is solid, so there is a definable map from N onto M. So again, we are done. And the third case is that N is a model of theory of M0, and M is a model of theory of MA. But then M is actually a retract of a model, which is a model of theory of MA, is a retract of a model of a theory of M0, which contradicts the lemma, the third lemma. So we are done. So we need to prove second and third lemma. So let's start with the third one. So we will prove that if we have two models, M and M is a model of MA, and N is a model of M0, then M is not a retract of N. Okay. So first we claim that there is an M-definable isomorphism from V omega of M onto V omega of N. As I said, the empty set is definable in M. Similarly, it is definable in N. Actually, N is more or less V omega plus empty predicate. Okay, so now we claim that there is M-definable isomorphism between these two structures. So again, we can think about the structures more or less as a models of Peano arithmetic. And actually, we can. These are such models of Peano arithmetic that, for example, in case of M doesn't see any cuts, any proper cuts in this model of Peano arithmetic. So basically, these are kind of natural numbers of M, and similar for N and for M star. Okay, so because there is no definable cuts in these natural numbers of M, and we have a notion of sequence if M, we can actually define an embedding from these natural numbers onto an initial segment of the natural numbers of N. Basically, we can map 0 to 0 and then make a inductive definition. Similarly, because N interprets M star, it can embed its own natural numbers onto an initial segment of natural numbers of M star. We can also compose these two embeddings to obtain an embedding from the natural numbers of M onto an initial segment of M star. But there is a definable isomorphism between M and M star, and this is definable in M isomorphism. So there is a definable isomorphism in M from the natural numbers of M onto the natural numbers of M star. So we can, using this isomorphism, transfer these cuts to M. But there is no definable proper cuts in M, so both these cuts has to be non-proper. So that means that both these embeddings has to be onto. So that means they are both actually isomorphisms. So we are done with this point. Okay, so now we claim that there is a sentence alpha such that for every model that satisfies alpha, it is reasonable there is a reasonable notion of V omega in this model. And if we know that this V omega in this model is actually isomorphic to the real V omega, then this model satisfies the theory of M0. And this is pretty trivial. It's like saying that there is a finite sentence in the language of arithmetic such that we have notions of addition, multiplication, 0, 1, 0, 1, and order, such that if we take the structure satisfying this sentence and natural numbers with this model with these operations are isomorphic to the real natural numbers, then this model satisfies the theory of natural numbers. So here we have a similar statement. So basically, in the context of arithmetic, we can take as a alpha, for example, PA minus. Yeah, if the model described by PA minus, if the natural numbers in the model described by that in the model that satisfies PA minus are isomorphic to the real natural numbers, then this model satisfies the theory of natural numbers. But now, using these 2 points, the previous and this, we can actually, without loss of generality, assume that the first model is isomorphic to MA. And the way we can do this, so, okay, we have a model M, which is a retract of N, which is a retract of N. So in particular, N satisfies alpha. So in the theory of M, it is true that there are parameters such that these particular formulas, which are taken from I1, so there are parameters such that I1 gives us an interpretation of alpha, and such that I1 composed with I2 gives us an interpretation of isomorphic copy of the universe, where this isomorphic copy, where this isomorphism is given by some other particular formula with some parameters. So the point is that already on the level of the theory of M, it is visible that we have such a situation that this model interprets model of alpha, which interprets isomorphic copy of the universe. Okay, but M satisfies the theory of MA. So already in the theory of MA, this situation is visible. So actually, if we have 2 models of these theories, such that the first is the retract of the second, then actually we have MA is a retract of a model of a theory of a theory of M0, because this is present on the level of a theory. Okay, so if we know that M is isomorphic to MA, then actually N is isomorphic to M0. And this is basically because we know that V omega of N is isomorphic to V omega of M, which is, in this case, actually just isomorphic to V omega. And if we know that V omega of N is isomorphic to V omega, then we know that N is actually isomorphic to M0. Okay, so let now A be the list of parameters from A which are present in A1 and in this isomorphism. Without loss of generality, we can assume that these parameters are all atoms. Basically, we can assume this because every element of MA is definable from atoms. Okay, so now we claim that there is a non-trivial automorphism of M that fixes these parameters. And this is not hard. Well, let's take an p atom. Okay, so first, find such a prime P that among these parameters there are no p atoms. Now take these two p atoms and just define defined an automorphism based on the fact that we just swap these two p atoms. So we define an how it's called permutation. So we define a permutation of A such that this permutation changes only one p atom with another p atom, and this extends to the automorphism of MA because MA is basically cumulative hierarchy built on these atoms. Okay, so there is a non-trivial automorphism of M that fixes A. So now we claim that this automorphism generates a non-trivial automorphism of N, and it will be a contradiction because N is basically isomorphic to M0, which is basically more or less the standard model of arithmetic. So it has no automorphism. Okay, so we need to prove that this automorphism generates a non-trivial automorphism of N. So we have M, inside we have N, and inside of M we have M star. And we have this automorphism, which is non-trivial, and which fixes parameters A. So now, because this automorphism fixes these parameters, so we know that it fixes the domain, maybe not fixes, it preserves the domain of N. It also preserves the equality relation, equivalence relation, which gives us equality on N, and so on for other symbols. So it generates an automorphism of N. Because in N, every element is definable with parameters, so we can actually assume that this interpretation, which gives us M star, is actually an interpretation without parameters. So this automorphism of N generates an automorphism of M star. Namely, it preserves the domain of M star and preserves all the relations. Okay, so but this automorphism of M is non-trivial. And there is a definable in M from these parameters, which are fixed, mapped from M onto M star. So this automorphism moves some elements in M star. So this automorphism has to move elements which represent these elements in N. So this has to be a non-trivial automorphism of N, which is a contradiction because, as we said, N is more or less the standard model of arithmetic. Okay, so we are done. So we proved that if M is a model of theory of MA and N is a model of theory of M0, then M cannot be a retract of N. Now we will prove that both these theories are solid. So first we can notice that this theory of M0 is solid, and this is because basically theory of M0 is synonymous with the theory of natural numbers. So in particular, it is bi-interpretable, and solidity is closed under bi-interpretability. We know that Peano arithmetic is solid. Solidity is closed under extension, so theory of natural numbers is solid, so theory of M0 is solid. So now we want to prove that this theory is solid. Okay, so let's take two models M and N of this theory and assume for contradiction, and maybe not for the contradiction, let's assume that M is a recheck of N. We want to prove that there is a definable in M map from M onto N. So similarly as in the previous proof, we can show that there exists an M-definable isomorphism from V omega of M onto V omega of N. Again, basically in M we have something that M thinks these are natural numbers, and similarly in N we have such a thing. So if M is a recheck of N, then we can define this map between these natural numbers. So we have this isomorphism. Similarly, as in the previous proof, there is a sentence beta such that for every model of beta, it is reasonable to talk about V omega in this model K. And if we know that this V omega of K is isomorphic to V omega, then we know that this model of theory of MA is that this model is a model of theory of MA. So similarly as previously, without loss of generality, we can assume that M is isomorphic to MA. So in this situation, we know that N is actually also isomorphic to MA because we know that V omega of N is also is isomorphic to V omega of M, and the model of theory of MA is determined by its omega, because basically our theories say that there is countable infinite set of atoms, and we build cumulative hierarchy on this set of atoms, and we put some relations on these atoms, and this is based basically on the notion of finite sequence. So, and notion of finite sequence is given by V omega of this model. So at least externally, M is isomorphic to N. So now we want to show that M is actually definably in M isomorphic to N. So first, we claim that there is an M-definable bijection from the atoms of M onto atoms of N that preserves the property of being a p-atom for every prime p. And this is enough because MA is basically V omega of A. So if we have bijection between atoms that preserves this property of being a p-atom, then this can be extended definably to the isomorphism between whole structures. Okay, so let I1 and I2 be the interpretations, and these interpretations, and H be the isomorphism. So first, without loss of generality, we can assume that both interpretations are identity preserving, by which I mean that the equivalence relation, which gives us equality in these interpretations, interpretation, is actually identity. Why we can do this? Well, we can use something which is called the Scott trick. So if we have an interpretation and we have equivalence relation, which gives us this identity, then we can take, okay, so every element, so let's take an equivalence class of some element. Then for every element of this equivalence relation is basically some finite set with places for atoms. So this is a skeleton plus atoms. So we can map skeletons to natural numbers, basically to codes of the skeletons, and choose this skeleton which has the smallest code. And so now we choose a finite subset of elements from this equivalence class, because we choose a skeleton and we can only change atoms inside of this skeleton. So now we can just take a subset consisting of all of these sets, because this is a finite set of finite sets. So we can change slightly this interpretation such that identity is really identity. Okay, so now let A be the list of parameters of I1 and of H. And without loss of generality, we can assume that it has some closure properties, namely that, and some other properties, namely that all these parameters are atoms of M. If X and Y are P atoms and X is in the list of parameters, then Y is also in the list of parameters. This is because there are only finitely many P atoms. If X is a parameter of I2, then every P atom from the transitive closure of the transitive closure in M of X is in A. This is basically something which we will use to say that if we have an automorphism which fixes these parameters, then it fixes also a parameters of I2. Yeah, so basically, in a sense, this first point say that A contains a parameters of I2. Okay, so now we want to define map from atoms of M onto atoms of N. So let X be a P atom that is not in this list of parameters. Then we claim that an automorphism orbit of the image of this element under this isomorphism is of cardinality P. Okay, so we want to prove this, that this an automorphism orbit is of cardinality P. Okay, so we have M, inside we have N, inside we have M star, we have X, and it is mapped onto H of X. We want to prove that the automorphism, an automorphism orbit of this element, as seen from the perspective of N, is actually of size P. And basically, we can do this also because we know that both these interpretations are identity preserving, so this element is really represented in N as a single element. Okay, so X is a p atom, so here we have other p atoms, and say these are all p atoms. So we can use H also to transfer these p atoms to M star. And now, if we have an automorphism, so first, we can notice that there is an automorphism which fixes parameters from the list and that moves elements, these p atoms. This automorphism preserves the domain of n and preserves the domain of m star. So it generates an automorphism of n and it generates the automorphism of m star. Okay, because this isomorphism A is defined with the use with the use of parameters that are fixed. So this automorphism is also non-trivial here. So these all p atoms have to be in the same n automorphism orbit, because automorphism of n generated automorphism of n, and this automorphism we proved that swapped these elements. So all of them need to be in the same automorphism orbit. So this automorphism orbit has to be of size at least p. So say we have an element which is also in the automorphism orbit of this element, but is maybe not a p, maybe is not an image of a p atom, so it's not here. But being a p atom in this interpretation is a definable thing. So if this point is in the same automorphism orbit as this, and this is a p atom in this interpretation, so Y also have to be a p atom in this interpretation. So actually it has to be one of these atoms. So we proved that there are at most p elements in the n-automorphism orbit of this element. Okay, so we proved that n-automorphism orbit of the image of X is of cardinality p. Now, by some combinatorial considerations, the set of atoms, okay, so if we take H of X and we take set of atoms from the transitive closure in A of H of X, and then this set of atoms has to be of the particular form, namely, there might be some parameters from our list. Well, actually, not directly from our list, but don't complicate it. So we have some parameters. Maybe we have, for some primes, we have all Q atoms for these primes. So yeah, and similarly in the second, it looks similarly in the second case. And in first form is the following. We have only one p atom here. And the second form is that there are all but one p atom. The point is that if we have X, which is a p atom, then it is represented in N by a set such that in the transitive closure of this set, there is one special p atom. So we can map this X onto this atom. And actually we can do this also because this form is the same for every X that is a p atom. Okay, so what was the structure of the argument? We noticed that the image of P atom has to be represented by a set of particular form of a form of the form by such a set that from this set we can define a p atom in N, and we use this basically to define this map. Okay, so we are done with this proof. Okay, so we prove that there is a solid, there is semantically tight, but not solid theory. Actually, this theory is also not needed. It can be seen from this proof. Formally, it wasn't a subtheory of ZF fin plus TC, but as I said, we can find a bi-interpretable theory with the theory which I have just described. Okay, so what now about other separations? Well, other separations are made similarly.
Piotr, can I ask now quickly? I didn't follow everything with details, but where did it matter that p's were prime?
Here, by combinatorial
Oh,
consideration.
so that's hidden here.
Yeah, so
All right.
we know that n automorphism orbit of some set is of cardinality p. So we from this derive that the set of atoms which are in the transitive closure of the set has to be of particular forms. So it has to be of the form all atoms of some types, p types, q types, some elements from the parameters, and either exactly one element which is a p atom, or all but one elements which are p atoms. So there is one p atom which can be defined from this set H of X.
All right.
Yeah. And here we use this by combinatorial considerations. Yeah.
All right. Thanks.
Yeah. Okay. So now what about the remaining separations? So basically the idea is similar. We take some models of ZF fin, which are constructed based on some models of finite of ZF fin over atoms with some predicate, which says that we have equivalence relations with prime equivalence classes of prime size, and we take some number of such models of this kind, maybe with some further adjustment, and we obtain what we need or what we want. Okay, so I proved that there is a uniform way to build examples in the context of ZF fin. So now we can ask, can we find a property of automorphisms that gives a similar result in the context of strong fragments of PA? So in the context of fragments containing, for example, I sigma 1 or well, some strong fragments. Probably we can find weak fragments of PA, which are some fragments of I delta 0, because as I said, already I delta 0 proves transitive containment axiom that transitive containment axiom holds in the Ackermann interpretation. Okay, so here is this question. We cannot adapt this directly, rather because, because here we use the property that the whole model is definable from the elements such that automorphism orbit of each element is definable and is of size is of prime size. So the question is, can we find a different property which works in fragments of arithmetic? Okay, and thank you for your attention. Here I put it some bibliography. Basically, the first position is the starting point of the whole considerations about these categories of theories and interpretations. In the second position, Ali and Ayat defined solidity, neatness, and tightness, and, for example, proved that PA, PA, ZF, Z2, KM are all solid, and that their finitely axiomatizable fragments are not solid. In the third position, Freire and Hankins defined semantic tightness. In this paper, there will be examples which I showed during the first talk, and one more example which I have planned to start today, but which I omitted. And the last position is a paper on models of finite set theories, which strongly influenced this talk. Namely, it is motivated actually by results which are in this paper. Okay, so thank you for your attention.